Okay, let's look at the next example. What we have here is a crate that sits on an inclined plane. They give you the theta of being 25 to the horizontal, and they give you the coefficient of kinetic friction. So having said that, you are asked to determine the acceleration of the crate if it slides down to the plane. And part B of the problem, if the crate starts from rest, 8.15 meters up along the plane. So you are on the hypotenuse, right? So to speak, yeah. What will be the crate speed when it reaches the bottom of the incline? Now, because we didn't do conservation of energy just yet, you're gonna have to apply the kinematics on the part B of the problem. But let's kind of worry about how we set up the problem first. So again, as a practice, let's go ahead and practice again. How do we deal with the inclined plane and how do we draw all our forces? It's a very good practice. And as I explained in a previous example, how do you find the angle between the components of the weight and the components of the weight and the incline, and how do you find the angle that comes from the base? So the first thing you know, remember you need to draw the system of coordinates. Then we'll go, the x-axis will go parallel to the incline. So maybe just like so. The perpendicular one will be your y-axis. And remember the corresponding angles that are formed where the sides are formed by corresponding sides. And if the corresponding sides are perpendicular, that's how you will find theta. So let's define our theta first. Right, you have the theta down here at the base. And what do you know? You already know that the weight is going down towards the center of the earth. So this is your weight force. We'll just call it M and then times G as a vector like so. That's correct. And now let's talk again about how do you find this angle. I know I'm repeating, but that's okay. So let's look at the angle theta. You know, it has two sides. One is the base right here. I'm highlighting it with yellow. And that is perpendicular to the direction of the mg of the weight. So you know that your new angle theta, that's going to be somewhere here. It will be one side will be defined by this yellow part, right? And let's pick here a different color, right? And make this other side that defines the angle theta, right, in an incline. Now that is perpendicular to the y direction that we have. So this kind of shows you now how to find the angle theta again, in case you forgot. Okay, so we have the weight. Now this crate is going to move down. So you have the kinetic movement going down. So if it's going down, I know I'm going to put here the system of coordinates. Remember, you always want to pick that so you don't get confused of where your pluses and minuses will be. So here's my y and here's my x. Yeah, if it's going down in the direction of motion, that means I'm going to have an acceleration. And remember, acceleration does not touch the body, free body diagram. So I'm putting it here on the side. So it shows the direction of movement of this. So here's my acceleration. And I obviously chose the positive direction in the direction of movement. So then you're going to experience a friction force, which is going to be opposite to the direction of movement. So here it is. It's kind of long. I don't think it matters right now. So here's the friction force. And again, this is the kinetic friction. Remember, you have a normal, and the normal force is actually the response of the surface, right, from the weight to the surface. So the response of the surface to the weight, so it will be perpendicular to the surface. Let me make it longer enough, I guess. So here's your normal force, Fn. And that's it. So normally you will not have the components, as I said before. This is your true free body diagram. But again, for practice, let's change colors here. And we're going to actually close our polygon or our rectangle, which is still a polygon, or quadrilateral. And it's a particular case of a parallelogram in the end, right? So I'm depicting my two components of my weight on the x and y axis. So now if you look, yeah, we get this component and this component. And now you look, what is it on the x-axis? On the x-axis is going parallel to the plane, and it's opposite to the angle theta, so that would be your sinus, so it's mg sine of theta. Yeah, and if you look at the y component, that's the adjacent side of theta, so that will be your cosine, right? So you have mg cosine of theta. All right. So with that being said, we can set up the equations, and this is a question of what equation? So we are talking here about a dynamic equilibrium, right? And so here you have to ask yourself, you're going to apply Newton's second law. All right, so let's look at it. We have the sum of all forces, which is your net force, on the x-axis, which is direction of movement, equals to the mass of the system, which is the mass of this crate or whatnot, times the acceleration of the system. Then you have the sum of all forces on the y direction. Then you have to ask yourself, is this body moving up and down? You know, does it fly off the plane? Does it go up? Does it go down? Right into the plane? No. So that means the acceleration here is 0. So that sum must be 0. So these two components should kind of be equal. So you know what? I'm going to actually fix this and make it longer enough to show that. Here's your normal force. Having said that, now it's more precise. And then don't forget about the definition of the friction force, yeah, which is defined, in this case, is kinetic movement, so mu k times the normal force. From here, you're going to get a system of equations, and you can probably find just about everything they ask. Let's look at part A. We're going to depict this and write them all correctly. So let's look at sum of all forces on the x direction. So you look who's going positive, right? So the component on the x right here, mg sine of theta, that's a positive direction. So we're going to start with that, mg sine of theta, minus the force of friction, and there's nothing else that comes along, is equal to mass times acceleration. Okay, from the second equation on the y-axis, what do we get there is that the normal force, which by the way goes positive, right, minus mg cosine of theta, that must be equal to 0. And the last one, force of friction, is mu k times force normal. Okay, so think about who force normal is. Look at equation number 2. So this is equation number 2. You can pull out your normal force, which is equal to mg cosine of theta. Now that I have this normal force, you can plug it into your third equation, and you obtain friction force is mu k times mg cosine of theta. Now that I have, so let me put some dots here for your equations, right? So we have equation 1, 2, and 3, and that's what they became after we developed them a little bit. So equation 2 becomes that, equation 3 becomes this, and now I'm going to use that information for the force of friction. I can take that and plug it into my first equation. And let's see what we get out of that. So results mg sine of theta minus, instead of friction, we have mu k mg cosine of theta. Now that is equal to ma. As you can see how nice is, you can see that the mass simplifies out by dividing with mass everywhere. Now g does not simplify out. Again, this is a very classic problem as well. So your job here is to get the acceleration, and we actually got that, right? So I should have put here that A was to find the acceleration, and the given part here was theta of 25 degrees. And on part B, if the length will be, okay, wait, we have a mu k also, 0.19. Okay, if the length is 8.15 meters, then they ask you final velocity or final speed at the bottom of the V bottom. We'll get to that in a moment. Okay, good. So here you can see acceleration is, you can actually show it nice by factoring out G. So you have G parentheses sine of theta minus mu K cosine of theta. Very nice. Now you can take your own calculator and plug in your numbers, and you will obtain a result for that. If you plug in 9.8 sine of 25, make sure your calculator is in degrees. Okay, minus 0.19 times cosine of 25. Okay, so I am actually getting 2.5 on this one, 2.5 meters per second square. Don't forget the units, of course, when you report your result. And please be nice, neat, and organized when you actually show the work. I think the work is more important than plugging numbers. As I said, don't jump on a calculator because you don't get credit for the work unless you show the setup. Okay, let's talk about part B. I'm going to do a simplified drawing here, but just to remind you a little bit, what are you looking at here? So honestly, the only thing, as I said, because we haven't done yet conservation of energy, you will see later how nice that is to know. You have an object, right, that moves from, let's say, this point right here to this point right here at the base. Yeah, we're going to call this V naught, which is 0 meters per second because it starts from rest. And this particular crate, it goes down a hill for this distance d. So this is the distance that is given to you on the problem right there. So I think what's important is for you to realize, hey, what kinematic equation I can actually use, yes? So you can have this distance d, or call it delta x if you may, which is x. So I'm going to even put it right here, which is delta x, right? X minus x naught. And this was your 8.15. And those are meters. So the question is, what is this V final here? So look at your kinematic equations. There is one that does not involve the time, and that's the Galileo formula, right? So you have your V final square minus your V initial square is equal to A times the delta X. Simply for us is D, right? The way I actually name it here on the picture. So knowing that your initial velocity is 0 because it starts from rest, then you obviously can see that you get your final velocity at the bottom of the hill will be square root of 2a times d. So the good part of it, they can ask you the velocity at any point during going down the hill, and they may give you only that distance. So this is the advantage of using the Galileo formula. Okay, so now let's kind of plug in our numbers. So 2 times our acceleration was 2.5, just double checking on this one. And of course, our distance was 8.15. Remember to put your units at the very end. Okay, and here I got 6.38. And those are meters per second. Feel free to round it to 2 sig figs here. So this would be 6.4 roughly meters per second. Okay, I hope this helps. And there's one more example coming up. So yes, make sure you watch this as well.